Welcome, as Dean said, to the first talk of the 11th Volcano Awareness Month. The title of the talk that I propose to give is called Transitions: What is Next for Hawaii's Volcanoes and HVO? And so what I'll do is give us a sort of recap of what happened in 2018, and here we are in a new year, thinking about what's going on at our two active volcanoes, Kīlauea and Mauna Loa right now, give you an update on status. And then talk a little bit about what, for both volcanoes, what we expect to happen next, as best we can tell, and end with a few thoughts on what is next for the Hawaiian Volcano Observatory, which, as many of you know, had to leave the park during the events of 2018 and is in the process of visioning its both physical self and personnel and program for the generation to come. So we'll start with a slide showing our setting here on the Big Island, especially for you visitors. The Big Island has 5 volcanoes above sea level, 3 of which have been active in historic times. Huala lie over here in the west, Mauna Loa, the granddaddy, covering half of the island, and then Kilauea Volcano, the young one, snuggled up here against the eastern flank of Mauna Loa. Kilauea, the one that has been so active for a while now. So, to set the scene, what was happening before 2018 here at Kīlauea Volcano? So think back to before the big events of the 2018 eruption, and what was going on at Kilauea is that we had a lava lake at the summit of the volcano that had been active starting in 2008. Here we are up at the summit at the visitor center, and just a couple of miles from us was this active lava lake that had spectacular views in the evening, such as this. In addition, out here on the east rift zone of Kilauea, about 12 miles from the summit, the long-running Pu'uo'o eruption that started in 1983 had been producing lava flows reaching the coastline for more than 30 years. So all of this changed very abruptly in the early part of 2018. And it seems sometimes like it was really just yesterday, when on April 30th, after many weeks of the volcano going through a pressurization phase, by that I mean we were noticing signs that magma was engorging the summit reservoir, the lava lake at the summit was rising and beginning to overflow onto the caldera floor. Pu'uo'o itself was rising and the level of lava was rising. The volcano was really getting full of magma. And what happened is, on April 30th, after a period of this pressurization, Pu'uo'o collapsed. The summit crater fell in, the lava column that had been filling Pu'uo'o vent drained into the core of the rift zone. And here in cross-section, showing from the summit all the way to the tip of the subaerial east rift zone, this cartoon illustrates that at the onset of the collapse, magma withdrew from this part of the rift zone and moved within the rift zone core to the east into the lower east rift zone. So all of this happened right after the collapse of Pu'uo'o. Things were started by that collapse event. We knew that something was happening and a significant change was underway because when Pu'uo'o collapsed, we began to see earthquakes migrating down the east rift zone towards the lower east rift zone, towards the subdivision of Leilani Estates and the related communities. The earthquake patterns were extremely clear. There was no mistaking it. Magma was moving underground towards that part of the rift zone. And so based on that, we issued a warning on May 1st, so this is about 24 hours after the collapse of Pu'uo'o, that an eruption was possible in that region of the lower east rift zone where magma was moving. And sure enough, on May 3rd, the eruption began. This is a short video clip taken on May 5th, so a couple of days later, but it's illustrative of the kind of activity that happened in those first weeks of the eruption down in the lower east rift zone. Blade-like bodies of magma reached the surface and formed a line of spattering vents, as you can see here. And the lava was rather viscous and sort of sticky. You can see these amazing bubble bursts and spatter not rising very high, lava moving away from these vents a few tens of yards. This was the activity that characterized the first few weeks. And then May 4th, so the day after the eruption started, all of you who live here remember May 4th very well. Around noon that day, there was a magnitude 6.9 earthquake on the south flank of Kilauea. Here shown in this map, the star shows the approximate location of the earthquake. Again, here we are up at the summit, and by that time the eruption site was down here. This earthquake was the largest earthquake here on the Big Island since 1975, and it shook really well. There was quite a bit of damage. The story I like to tell is that Janet and I missed the whole thing because we were flying in a helicopter at the moment of the earthquake down to the Lower East Drift Zone to see what was going on from the air. But we could tell something was happening because there was dust flying in the air and lots of radio chatter, of course. This earthquake happened at the base of the Kīlauea volcano pile. So this is a cross-section through the volcano, and the star here shows approximately where the earthquake occurred, where the volcano sits on the old ocean floor here at a depth of about 6 miles or so. And at that earthquake, what that represented was that the south flank of the volcano was actually moving suddenly to the south. It had been basically pushed in that direction by that blade of magma, that dike that was moving down the East Drift Zone, pressurizing and pushing the flank of the volcano towards the ocean. So that was the drama of May 4th. The eruption continued, started and stopped through the first part of May, but by late May things had settled down at the famous Fissure 8 that became the prominent cone that you can still see down there today. And this amazing river of lava traveled all the way about 11 kilometers to the ocean through these channelized features. And of course this went on for about 3 months and produced the devastation that we know happened down in the Lower East Drift Zone. On June 3rd, the lava flows first reached Kapoho Bay and began to destroy so much of that lovely community. And meanwhile, while this activity was going on down in the Lower East Drift Zone, big things were happening up here at the summit of the volcano. So for those of you who are visiting, if you were here at the start of this eruption in May of 2018, looking off towards Halemaumau, you would have seen these occasional explosions that look like this. These are the largest explosions that we'd seen at the summit since 1924. And this is a short video taken from the Volcano House just following what was one of 62 big collapse events at the summit during the period of the summer of 2018. So what was happening is that while that lava was erupting down in the Lower East Drift Zone, 25 miles away from the summit, the roof of the volcano was basically falling in steps because of withdrawal of magma from the summit reservoir complex. And each one of those collapses produced a scene like this, where the ground actually dropped 3 or 4 yards, and of course rocks were clattering down all the steep caldera walls, liberating dust that you see here. There were 62 of these events that happened over the course of the 3 months. And each time there was an equivalent of a magnitude 5 earthquake that was produced. And so residents in the summit area can well remember what that felt like, the ground shaking with regularity. This is an aerial photograph illustrating what was before and after the activity here at the summit of 2008, during 2018. This is the before picture showing the Halemaumau crater, about 1 kilometer across and 80 meters deep or so. After the activity, the collapse area around Halemaumau looked like this. It had about tripled in diameter and more than 5 or 6 times deeper than it was before. Again, as the roof of the volcano was collapsing downward onto the slowly evacuating magma chamber below. So this eruption was dramatic. It produced a lot of devastation. It was very tragic for a lot of people on the Big Island. It was tragic and challenging for HVO to monitor well and provide good information. But it was also a scientific gold mine, and we can't ignore the fact that we accumulated an enormous amount of information by tracking and studying that eruption. So what did we learn from all of that? And I'll say that we're just beginning to unravel a lot of those lessons. There will be people looking at these data for decades to come to understand more about Kilauea and volcanoes in general. But to hit on some of the high points of what we learned, some of you may remember that at the start of activity in May of 2018, we stood in this room and talked about what happened in 1924 at Kilauea, which was the last time that a lava lake had receded into the volcano and drained back into the magma chamber. In 1924, there were 3 weeks of explosive events that produced ash and big blocks. And we thought that that was because as the magma column drained into the volcano, that groundwater was able to flush back into the system and produce steam-driven explosions. So we talked about how that was likely to happen. Well, as the video showed you earlier, we did have explosions after a couple of weeks of activity here at the summit, but instead of being driven by groundwater rushing back into the hot core of the conduit, we now think that it was more likely volcanic gas accumulating and pressurizing beneath the rubble that was filling in that collapsing column and occasionally blowing out material to form an explosion. That groundwater was really not part of the process. And the reason we think that is that a lot of the material that came out was actually, magma itself. Lava was involved. Each time one of these explosions happened, there was a big burst of volcanic gas. So it seems more like gas was the culprit and not groundwater. Another important thing we learned down in the Lower East Rift Zone, and if you come to Matt Patrick's talk, which I think is next week, Carolyn Parchetta's talk in a few weeks, you'll hear about this. Because the eruption went on for so long, we were able to bring a lot of instruments out into the field, cameras, something called infrasound. We were able to use our drones to take aerial photographs of the lava channel, to bring all sorts of instruments to measure things consistently through that 3-month period. We saw patterns in the eruption that had never been studied quite in such detail before. And Matt Patrick and colleagues recently published a paper in Science that talked about these patterns. Basically, what was identified were 2 different timescales of surging or increases in output at the Fissure 8 vent. And these were seen in the channel because we had people watching and cameras filming the channel just downstream of Fissure 8. These 2 cycles were on different timescales. One had a period of 1 to 2 days. There was sort of a long wavelength up and down of output. And by output, I mean how much lava per second from the vent. And the other cycle was much faster. It occurred over periods of just 5 to 10 minutes, so a higher frequency cycle. By looking at all of the data and comparing it with what we were seeing elsewhere on the volcano, what Matt and his colleagues now feel is that these long wavelength, 1 to 2 day surges in output were absolutely responsive to the collapses going on up here at the summit. So even though the summit collapsing was 25 miles away, each time the roof of the volcano fell in those several yards, there was a pressurization of the magma system below, and that pressure pulse traveled through the rift zone core all the way down to the Lower East Rift Zone to cause a surge in output. This has not been seen in such detail before really at any other volcano. There had been hints of this at an Icelandic system that was quite similar, but we were able to really track this in detail. And it had implications for hazards because when we saw the collapse at the summit, we learned that within minutes, and certainly peaking within hours, we would see an increase in output in the Lower East Rift Zone. So we were able to be on the lookout for overflows of the channel or potentially a new breakout from the lava river. The faster cycles, the shorter time scale changes in output were likely due to very shallow outgassing processes. And the proposal in this paper is that the magma, as it's coming to the surface to erupt, develops gas segregation areas or foamy regions. And so for a time, the magma coming out might be extra rich in gas and more foamy, kind of like the head of a beer or a soda can when you pop it out. And during those times, you actually have less molten material flowing into the channel. Other times, the magma is less frothy. It's denser and it will come out at a greater rate. So exactly what controls that frothiness and the change through cycles is still kind of a mystery, but it seems that that is what is controlling these very short-term outflow changes at the vent. So that was quite interesting to see, and only possible really because we were tracking things so closely for so long with so many tools. Another really important insight was looking at what was going on up here at the summit. And similarly, we have all these different tools that we were using at the summit. We had tilt meters, we had a laser rangefinder watching the retreat of the magma column back down into the volcano. We had GPS at the summit watching the ground subside. And we had satellites tracking this from space. In particular, there's a radar satellite that comes over the volcano and takes a radar picture, comes over again and takes another radar picture. And you look at the difference between those two, and it tells you if the ground has gone up or down or how it's moved. So all of these tools allow geophysicists to look very carefully at the collapse process and really make a model of what was going on underground to cause the collapse that we saw at the surface. So this collapse through time is shown in that little movie. Now that's essentially that process of the roof of the volcano falling in as the magma chamber below is draining and material is flushing into the rift zone to be erupted 25 miles away. So by looking at the changes at the surface and the shape of that collapse and modeling all of the data from these different instruments, Kyle Anderson and his colleagues have determined that the collapse at the summit started very early in the withdrawal process. Only a few percent of the volume of that summit magma reservoir, which is about a mile below the surface here, was drained by the time the collapse began. And that was really surprising to us in retrospect. I think the paradigm had always been that you had to have wholesale withdrawal, really emptying of that chamber before the roof would start to fall in. And that was clearly not the case. So that was an important result. And the final lesson or insight I'd like to share is, it was just recently published in a paper by Cheryl Gansecki, a UH-Hilo professor and colleagues, and it has to do with the chemistry of the lava that was coming out in the eruption down in the Lower East Drift Zone. So this is a cross-section through the volcano. Here's the summit area again, we're right up here, and here's the eruption site down in the Lower East Drift Zone. This cartoon is showing a schematic of what we think the volcano looks like in cross-section. Here's the summit reservoir complex, a shallow region and a deeper region, and then the core of the molten core of the rift zone that heads down to the east cape of the island. So here's Pu'u'o, and what Cheryl and crew discovered by looking at the chemistry of lavas that we sampled almost every day over the course of the eruption is that the first material that came out was actually material that had been stored in the rift zone for many, many decades, maybe going back 100 years. And we knew that based on the chemistry, the chemical analysis, the temperature, the way it behaved at the surface. But why did it erupt? Because there was fresher material coming into the rift zone beneath it, adding heat and gas and causing it to be remobilized to the surface. And then as the eruption progressed, these pockets of older material, they mixed with fresher material and ultimately were flushed out such that the final material coming out of the volcano in the eruption was very fresh material that probably came from up the rift zone and even the summit storage area. So that progression through time was very clear because we had so many samples taken in sequence and very rapid analyses. This is not a new idea. This has been thought of for many, many years at Kilauea, but it's really been shown in exquisite detail because of the sampling and analysis of 2018. And just to show some of the data, this is a plot through time of the eruption. So this is days since eruption start. And on the right-hand side here are magma temperatures inferred from chemistry. And what you can see is that the first material out, these colors, were lower in temperature from 1060 degrees centigrade up to 1120. This is the opening sequence. This is Fissure 17, for those of you who remember that. And then by late May, things got hot. Things were above 1140 degrees centigrade and stayed there pretty much for the rest of the eruption, with the exception of a reactivation of one of the fissures late in the event. So the chemistry and the temperature all told this story of old material coming out first and then flushed with fresher, hotter stuff through the eruption. So that's the recap of 2018. What's Kilauea doing now? Well, the bullet points are here coming up. First of all, magma is returning to the East Rift Zone and to the summit area of Kilauea. And that's best shown in this interferogram, which is a graphic produced from one of these radar satellite imagery passes I talked about. Two passes compared, and these psychedelic fringes here are bullseye patterns, are basically showing an area of uplift. Take my word for it, that's the way that these radar images get combined to show that process. And you see the bullseye right over the Kilauea summit, because the ground there is rising slowly as magma is coming back into the system. And also down here, here's Pu'u'o in the Middle East Rift Zone is also rising as magma is accumulating in the summit. The accumulation area in the East Rift Zone actually extends down towards Highway 130, which is just right at the edge of the slide here. So it's really a broad region in the Middle East Rift Zone that's inflating or reflecting this accumulation underground. Another important point about Kilauea right now is that the gas emissions are at the lowest level they've been in a long time. Just last week we measured only 40 tons a day of sulfur dioxide coming out of the summit. In the lava lake time, the numbers were up around 5,000 tons per day. So the magma is deep enough that we're not seeing a lot of sulfur dioxide at the surface. We can see that same process if we look at the GPS data for the summit of Kilauea. This is a station up near the old observatory. And this is a plot going back from February of 2018 to today. Basically focus on the fact that there's an upward trend to this plot. This shows that there's been about 15 centimeters of ground uplift. So what's that? It's about 6 inches or so uplift of the ground over at the old observatory as the summit is reinflating. And the same thing out on the East Rift Zone. These are other stations, this one near Pu'uo'o, this one a little further down Rift. I should have pointed out that this big drop here is to the eruption in 2018 when things were collapsing. But the East Rift Zone station has risen about a little over 10 centimeters and Joka up just a few centimeters down here on the, I'm sorry, got that backwards. Pu'uo'o is up about 20 centimeters and Joka up about 10 centimeters. So the volcano is reinflating, meaning magma is coming back into the system. The other big change at Kilauea that many of you are aware of is that we now have water in the summit of Halemaumau, or the summit crater, the Halemaumau crater. And here's a photograph from one of our web cameras that you can find on our website showing the new collapse region with a little, well, it's not little, it looks little because it's so far away, but this is the rising lake of water. I'll tell you how big it is in just a minute. This is a plot of the depth of that lake of water. We've been going out a couple of times a week to measure the distance down to the lake and inferring then the depth or the rising elevation of the surface. So this is a plot from late July up to just a few days ago. It's now 75 feet deep. And the lake itself is this big. It's 280 feet by 620 feet. So it's a football field wide, 2 football fields long, and of course it's getting bigger all the time, rising still at about a yard a week. This is a video, a sped up time lapse from a camera that was positioned on the east rim of the inner pit when our crew was down on the down drop block recently. And of course it's much faster than real, but it's showing some interesting things, the steaming of the surface. You can see some motion of the cloudiness in the lake. You can see that some areas are greener than others. These greener areas we think are areas where fresher water is coming into the lake, and then it's being mixed with minerals that are precipitating, causing the reddish brown color. It's a very dynamic lake. And it's hot. So this is a thermal image taken from the helicopter, but this is what the image is showing here is temperature of the lake. It's about 70 degrees centigrade, so that's 158 F. That's just about scalding. And that seems to be a pretty constant temperature of the surface of the lake. It's probably hotter with depth. So what's going on with this lake? If you can come to Matt Patrick's talk next week, you'll hear about this in great detail. But in a nutshell, here's what we think is happening. Back when the lava lake was active, of course, it was very hot. There was 2,000 degree Fahrenheit lava coming up to the lake. And it basically was forcing all the liquid water into steam or away from that conduit system. And so the water table was back. And there was no liquid water reaching the conduit. Well, in 2018, the lake drained. The summit fell in. A big deep hole got punched down and basically intersected the water table, which has now returned because the heat has changed. It's not so hot anymore with that column of magma. So that's what we think is happening. And one question, of course, is how deep do we think it could get? If it becomes as deep as water in a research drill hole, it's about a mile to the south of the lake, this dotted line shows how deep it might get. So that's going to be a pretty significant water body. Unfortunately, you can't see it unless you're really right on the rim. But we've got a lot of web cameras looking down there, so you can watch it. We did sample the lake water, which of course is something lots of people were interested to do. We used an unoccupied aerial vehicle in late October with park permission to do this, and we've sent the water off for analysis, and these are some of the things we learned. First of all, it was a very atypical lake for volcanic crater lakes. We expected it to be quite acidic, and even though it is acidic, a pH of about 4.2, a lot of volcanic crater lakes are closer to 1 or 2. And we think that's likely because it's reacting with some of the lava rocks along the bottom of the lake and the walls, and it's being buffered somewhat. It appears to be groundwater or rainwater leaking in, as we suspected. There's a lot of volcanic gas getting dissolved in this lake, and we see that in the sulfate chemistry, as well as some of the precipitates that were brought out of the water in the lab. The water is a little different than the Keller well water, which is to the south, the research hole, and we're still trying to figure out what that means. It's probably a mixing with waters along that path from the well to the lake, so it's not exactly the same. And the gases in the atmosphere around the lake were actually not too high. Carbon dioxide and sulfur dioxide concentrations were not great. a lot of that gas is going into solution in the water. So what we want to do now is keep sampling with some periodicity to watch for changes in that lake chemistry. Of course, another really important question is, what are the hazard implications of having a lake inside Halemaumau? The presence of water, whenever you're talking about hot magma potentially interacting with that water, do allow for the possibility of explosions. But we think at this point we won't have explosions from magma-water interaction unless magma rises very rapidly into the lake. And we see no sign of that happening, and we would expect to see changes before that happens. And even then, we're not sure, given the geometry and the volume, that there would actually be explosions. But it is a possibility we have to consider. Especially after the New Zealand eruption a few weeks ago now, people have asked if that could happen here. And our answer is that it's a very different system here. This is a much leakier volcano. There's no sign that the system is sealing and pressurizing under some sort of impermeable cap, like happened at that White Island volcano in New Zealand. Our volcano is not at this this water lake is not at sea level. It's got a different composition. The rocks are of a different chemistry, so the minerals precipitating are not high in silica, and they're not likely to clog up the pore spaces in the same way. So the short answer is we don't think we have a White Island situation developing here. But we can't completely rule out the possibility that there will be sudden steam explosions at some point. So this is something we're considering as we go forward. So what's next at Kilauea? Well, magma is returning to the system. That we know for sure. But it's still possible we'll have many years of quiet before the next eruption. Many years, a year, 5 years, hard to say. Based on past patterns following big events like 2018, it's most likely that the next eruption would be in the summit area. That's about all we can say with certainty. Okay, let's move on to Mauna Loa, the other volcano that's always on our mind. Mauna Loa, too, is accumulating magma in its shallow reservoir system. You may remember we went through a period from 2014 to early 18 where this was happening. The volcano was inflating as magma was entering the reservoir. We saw higher earthquake rates. And then, interestingly, in 2018, right around the time Kilauea erupted, things went a little quiet. And that may not be coincidental. Well, that trend reversed itself in late 2018, and now we are again seeing Mauna Loa inflate. And because of that, we raised the alert level for the volcano back in July. And that trend has continued. Here are some data to show that. This is a GPS stations at the summit of the volcano. Here's Moku'uwe'uwe'o caldera. And this is a GPS plot for the station at MOKP and MLSP on the south side of the caldera. And again, basically note that the upward trend of these GPS plots through time reflect the rising of the ground, not a lot, 5 centimeters, 10 centimeters or so, a few inches over this 5-year period. All of that reflecting accumulating magma in the shallow reservoir. At the same time, we're seeing increased earthquake activity, just like we did between 14 and early 18. Here's the summit of the volcano outlined here below this cloud of shallow earthquakes, which also extend into the upper southwest drift zone, and then there's a cluster here on the west. So these earthquake patterns have been persistent, and they continue today. And what's interesting about them is that they're similar patterns that we saw prior to the 1975 eruption at Mauna Loa and 1984 eruption of Mauna Loa. So it's following some of the same patterns, but we cannot say that we're a month away, a year away, or 10 years away from an eruption. It's just we don't know that well enough. We would expect to see significant changes in the rates of these earthquakes prior to an eruption. So we expect a fair bit of warning. Another way to look at that earthquake activity at Mauna Loa is in this plot. This goes back to 2010, and these are earthquakes per week underneath the summit of the volcano of all magnitudes. Here's the period in 2014 when things started to perk up, and we went to alert level advisory, and we stayed there for a few years. Here's that quiet-ish period in 2018 when we were below 50 earthquakes a week, and then in late 18 and into 19, you can see we've had an increase in the weekly average earthquakes with some big spikes. So this is why we feel comfortable saying we're above kind of a long-term quiet that persisted before 2014. What does this look like in cross-section? This is an old plot, but it still holds. This is a model result done by Ingrid Johansson at HVO back in 2017. So this is a cross-section through the volcano, Mauna Loa. You can imagine the summit is up here. We're looking into the volcano. This dotted line is sea level. And the colors here, from very dark to light yellow, you can imagine that this represents the amount of opening that has occurred within the volcano as magma has moved into it to fill and engorge that shallow reservoir system. So we've had up to a meter or about a yard of, basically expansion within that part of the volcano to accommodate this incoming magma. That explains the summit deformation pattern. And this cloud of circles here are some of the earthquakes that happened in the period 2014 to 2017. They all occur kind of at the top of that region of expansion, which is what you'd expect where the rocks are being stressed and strained by this accumulating magma. What's next for Mauna Loa? More of the same, most likely. There's really no sense that that trend of inflation and accumulation is about to change. One of the interesting questions we're pondering is what is the impact of the Kilauea eruption in 2018 on Mauna Loa? Clearly the Kīlauea volcano relaxed a lot in 2018. It collapsed. It sort of relieved some pressure on Mauna Loa. Does that mean that it's easier for Mauna Loa to erupt now? Can magma decompress more rapidly and come to the surface? Or does that mean it's less likely to erupt now because pressure's been relieved? We're not really sure what that answer is, but there may be an impact. An important thing I'd like to point out, though, about Mauna Loa is that damaging flank earthquakes are possible at any time. And the reason that's relevant is that prior to 75 and 1984 eruptions, there were moderate magnitude, 6.6 and 5.5 earthquakes months before the eruptions. So if we have an earthquake of that magnitude range somewhere on the flank of Mauna Loa, HVO will be at a slightly heightened state of alert or concern about the volcano. Preparation is key. Okay, well let me close with what is next for the Hawaiian Volcano Observatory. Many of you, I think, know that it was a very dramatic departure for us in 2018. We had to leave in a hurry as the building was becoming damaged and the threat of collapse or harm to people in the bluff area during the earthquakes and explosions was increasing. For the eruption, we relocated down at the University of Hawaii Geology Department for much of the summer, and then we've moved a couple of times since then. And we are now in the Ironworks building in Hilo, for those of you who know Hilo. We have two very nice USGS signs on the outside. And whereas my office had the unbelievably honorific view of Kilauea caldera out the window, now I look out on Hilo Bay, which is also very beautiful, but a very different view. And I'll point out that this building is smack dab in the tsunami hazard zone. But I'm on the second floor, and we know that in 46 and 60, the first floor was trash, but the second floor I think was all right. In any case, we are there, most of the staff are there now, and we'll be there for some years until new buildings are built. We also have a warehouse facility out in Kīlauea where our technical team and all of our stuff is being stored in a warehouse. So we're in a split facility for at least a few years until new buildings are built. If you've been reading the news, you know that Congress was very supportive of the fact that we needed a new facility. Our old facility is broken, and the decision was made not to relocate at the Oikahuna Bluff, to remove ourselves from the high hazard zone and to place ourselves in a better location. So the decision's been made to build a main science center down in Hilo. It's not just going to be HVO, it's going to be a USGS Science Center, so the biology office that's up here in the park will also be co-locating with us in Hilo. And no location's been chosen yet, although there's obviously discussion going on with especially the university for potentially co-locating on their campus. However, we must still be here in the park. HVO scientists want to be in the park. Our work requires us to be here quite a bit of the time. And of course, when activity resumes here in the park, which it will, we'll want to be here more often. And the park has made it clear that they would like us in the park to help advise them on the activity at the volcanoes going forward. So to accommodate that, we have additional funding to build a new field station in the park. It won't be the size of the old HVO building, and it won't be up on the bluff, but it will be in the park. And so The exciting thing is that we get to design these things from the ground up now, and there's been discussion already within HVO and with an architect about what is it that we need in these buildings to truly support our mission going forward for the next generation or two. So with new buildings coming, it's also an exciting time because we have lots of new tools and capabilities arriving. And I try to focus my happy thoughts on this when I get sad about not being up in the park anymore and missing being in Volcano. But we have many new things coming online. We have an unoccupied aerial vehicle fleet that we have, and we've trained 5 new pilots at HVO. And they're just unending uses for these things going into the future. Unfortunately, we've had a stand-down order from the government. We're not flying right now except for emergencies because of concerns about foreign hacking through these devices, but we're going to fix that here pretty soon and be using them more regularly. One of the things that happened in the 2018 eruption is that we've started to really use infrasound, this technique of looking at seismic energy that travels through the atmosphere, as a more standard tool, and it's proving really useful to helping localize where activity is happening and using as an alarm system for us to tell us when things are happening. So that's very exciting. We're exploring new ways to make our field instruments lighter and more robust. There are a few people in this audience I know who've carried around car batteries up at Mauna Loa summit to power these darn stations, and so we're experimenting with new lithium batteries which are lighter weight to try to reduce our footprint and save our backs. Cameras are just, as you know, becoming smaller and lighter and better, and the 2018 eruption saw our geologists trying many new both high definition and small game cameras out in the field to capture things that are ephemeral, and those are becoming more and more useful. We also have pretty regular use now of 3D printing to make parts for our instruments, components, and that's a very exciting development for being nimble in the future when we need to make new instruments on the fly. So lots more to come in that regard. And if I could just close by saying, in my view, I feel like HVO's future is very bright, even though we've had this traumatic departure from the place where HVO has been for more than a century. We have good funding right now to support our growth, both in staff and with equipment. And we, because of the 2018 eruption and the Pahoa lava flow in 2014, there's a lot of very good relationships with our emergency management partners in the park. And so I feel like HVO is in a good place to participate and respond to the next crisis, which could be Mauna Loa, could be Kilauea. And finally, my comment about no matter where HVO is, no matter where we are, you can be sure that it is part of your community. Thank you.